question now. So we'll try to use atomic radii data to calculate the Coulombic force of attraction between two charged ions, this time magnesium and oxide. And as part B, we'll try to determine the repulsive force value as well. Okay, so take a moment to think about what your strategy would be for this problem. Pause the video as needed and resume when you've had a chance to sort of think forward about your approach. And if you want, you can even compare your notes to our solution that's coming up in the next part of the video. Okay, so what we'll do here is first get a depiction of what's going on. So we have our two ions in question. They have a nucleus at the center of these spheres. We know that the smaller one is going to be the magnesium cation. We know that the larger one is going to be the oxygen 2- oxide anion. And that we know their radius from the appendix information also listed on screen. So the R magnesium is right here. And the radius of the oxide is right there. And so we have from our previous equation that the Coulombic force of attraction, Fc, was equal to K naught, proportionality constant, times some information about the charge and the number of charges. So we have the Z of the magnesium 2+ times the charge of an electron, and then we have the Z of the oxide 2- times the charge of the electron. That's our numerator, and this was going to be divided through by the space between the two. On our previous equations, this was A squared. So the space between the two was from nucleus to nucleus. So it hopefully follows, therefore, that A is going to be equal to the radius of the magnesium 2+ plus the radius of the oxide 2-, as we see here. So that is A right there. Okay, and I mentioned earlier that we would like this information in meters so that we can handle the unit cancellation properly. So that is A here is going to be equal to 7.8 times 10 to the -11 meters plus the 1.32 times 10 to the -10 meters. And therefore A here has a final value as the sum, which is 2.10 times 10 to the -10 meters. Okay, so we're now armed with the information ready to go into the denominator. So this is great. We're now have everything I think we need to calculate the Coulombic force of attraction between these two ions. Okay, so we saw before that the proportionality constant was 9 times 10 to the 9 volt meters per coulomb. The next parentheses piece of the numerator is the charge value as an integer with sign for the magnesium. So this is going to be +2 and then times the charge of an electron, 1.6 times 10 to the -19 coulombs. And then we're going to multiply this by the integer number representing the charge of the oxide. So this is going to be times -2 times 1.6 times 10 to the -19 coulombs. And our denominator is going to be the square of the distance between the two, which of course was the sum of the radii. So that's going to be 2.10 times 10 to the -10 meters and squared. Okay, so we'll first take a look at what's going to happen with our units. So we're going to end up with coulombs squared from the latter two components here. And we're going to divide away one of those coulombs. So we'll end up with a coulomb in the numerator piece. And we'll also end up with meters squared in the denominator. And so we'll cancel one of those will get canceled by the numerator of the meter in the top here. So we should end up with units that are volt, coulomb per meter. Okay, and now we can go ahead and calculate the rest. And so the product of the numerators, and then after dividing through by the sum of the distance between the two, is 2.0898 times 10 to the minus 8 volt coulomb per meter. Kind of a funny unit. And let's see if we can think about how this might equate to units that we're used to for force. If you might recall, you know that from earlier courses that work is equal to force times distance. Work, of course, has energy units in joules. So putting units here, joules will come from newtons times meters from that. Okay, so we have that information. We also know from earlier work that 1 volt was equal to 1 joule per coulomb. And so if we transform these units below from volt coulomb per meter, we can first input the latter information. So we'll transform volt coulomb per meter to be joule per coulomb per meter, and that'll give us joules per meter as our outcome. And you can see here that a newton is equal to 1 joule per meter. So this is all to say that a volt coulomb per meter is equivalent to a newton. So the answer, respecting sig figs, is going to be 2.1 times 10 to the minus 8 newtons of Coulombic force between the two. Okay. Now for the next part, we'll consider part B here. So let me just clean up the slide for us. And consider how we handle part B. So part B says, what is the force, the repulsive force? So before searching back for a repulsive force, we should actually just consider the case. So we're looking to understand the repulsive force when we have the ideal bond length between the two ions in question. So that is where the force of attraction is balancing the repulsive force. So we just learned a moment ago that the force of attraction, or the Coulombic force, was equal to 2.1 times 10 to the minus 8 newtons. And that was the force of attraction bringing these two together. And of course, that has to be equally matched, but opposite in sign, to the repulsive force, which is going to be repelling the two away from one another. So if the Coulombic force here was positive, then the repulsive force should be the opposite sign, negative 2.1 times 10 to the minus 8 newtons. Okay. Check your previous work on part A. Note the signage here. So we should have had a minus sign in the numerator, canceling the minus sign that was inherited from the -2 on the oxide. Okay, so I may have forgot to highlight that in my previous discussion, but notice that we ended up with a positive value for force here. And we know that this should be opposite in sign as we go to the repulsive force for part B. Okay. So some of that is formalized here, the approach there to calculating FC.